Anyway, good luck with the talk, and I'll send you an email afterwards.
Thank you, Nick.
Yeah.
Chris, we're ready whenever you are.
Okay. Well, it is my great pleasure to introduce our cloak and speaker today, the distinguished astrophysicist Francoise Combes. She's an astrophysicist at the Paris Observatoire and also a cosmology professor at the Collège de France. And her long and distinguished career has been capped off last year by winning the CNRS gold medal. She started her research after graduating the École Normale Supérieure in quantum physics, but then moved into cosmology with the baryogenesis problem, and then became one of the early pioneers of millimeter astronomy. She found herself observing from a number of telescopes, millimeter telescopes in the United States, the McDonald 5 meter, the Kitt Peak 12 meter, where she discovered carbon monoxide in spiral arms of nearby spiral galaxies, Andromeda, M51 and M81. Very important early discovery. And at that time, she also observed at the Aerospace Corporation antenna, where she found that she was had to be escorted by guards. I don't know whether they're armed or not, but everywhere day and night. I don't know.
They were armed, yeah.
But that has been followed by a long and distinguished career using molecular lines to probe star formation and galactic processes, including galactic dynamics, as well as theoretical investigations of galactic dynamics with major findings as far as stellar bar formation. And then as well as probing dark matter in galaxies, both cold molecular dark matter and other forms of non-baryonic dark matter. So I just wanted to share a wonderful picture that was published when Francoise won the gold medal, and that is right here, showing her in a very elegant place, the Observatoire de Paris. As she points out, the oldest observatory still operating from the not quite dark skies of Paris, but it's a beautiful telescope and a great historical institute. And so we wish her the best and in what is continuing to be a wonderful career. And we are extremely grateful that she has made time very late in the day in Paris to give us a talk on the molecular lines from the galactic center and what it tells us about feedback and AGNs. So, Francoise, why don't you take it away?
Okay, you see my screen. So thank you very much to invite me, and I can now present you our recent ALMA results about galactic nuclei. I will try to show you that we have now the resolution to go to the center of galaxies and to try to check the paradigm of AGN, that is the dusty torus that obscure the Seyfert-1 to become Seyfert-2 and all this unification. But just in the preliminary, yes, preliminary consideration. Okay, I want to get rid of this. Okay, so I want to tell you about what we think now is in the center of AGN. It's a recent image by Honig in 2019. And you see here that the dusty torus is no longer there. In fact, it was a paradigm, but it's no longer there. You have here in the center the AGN, the engine, which is an accretion disk around the black hole. It's a big blue bump here, very hot gas accreted by the black hole. And then with the temperature, you have no molecules or no dust because it's sublimated. And then you have a disk. But what we have learned about from the mid-infrared interferometer is that the dust is not in a dusty torus, it's in a polar outflow. In fact, it's outflowing because there is not only inflow but outflow. And this dust is pushed by a wind. The wind, essentially, when you have a high luminosity AGN, that is pushing by radiation pressure the gas and the dust, that you have still some accreted molecular disk and the molecular theory that I will speak about. And you have here, for instance, H2, which is highly excited. You have H2O mesers, and here is where we find the molecules. So here I will outline here the feeding. Angular momentum transfer is due to gravity torques because in the 10 parsec scale that I will describe here, you still have not enough viscosity of the gas. You need some gravity torques to feed the gas inside the AGN. So I will describe the dynamical feature, the nuclear bars and spirals that we have discovered with ALMA. Second, I will speak about the feed because you have both inflows and outflows, I mentioned. And in general, you have some winds when you have high luminosity galaxies and AGN radio jets when you have low luminosity galaxies. So I will describe some. And finally, I will describe what we've discovered is the molecular tori. And in general, most of the galaxies have these small things at 10 parsec scale. And they are decoupled, meaning that they have not the same orientation than the main disk. So first, I want to recall some big features that we will need to understand the rest of the presentation. That is what is occurring in barred galaxies. When you have a bar in a galaxy, you have, for instance, a bar in the horizontal picture here. You have stellar orbits that are parallel to the bar and then perpendicular each time you cross a resonance, for instance, Lindblad resonance inside, which is called inner Lindblad resonance, or the corrotation, or also the outer Lindblad resonance. Each time you have orbits that change by 90 degrees their orientation. So this is for the stars, which are not dissipated. There's no collision between stars. But when you have gas, of course, it tends to follow these orbits. But then gas is dissipative, so you have collision between the gas, and the orbits of the gas will turn gradually by 90 degrees and not perpendicularly, and you have a spiral. And this means that the stellar bar will exert some torques on the gas, and the gas will be driven in and will stall at the resonance. Here you see in the top right a picture of a galaxy, barred galaxies in B minus V colors. So you see in black the blue colors, and you see the star formation that occurs at the resonances and outer resonance, the corrotation, and the nuclear ring. But you see the gas is piling up in the nuclear ring, and sometimes it is stored there and doesn't go to fuel the AGN. So what you need then is an embedded structure, that is a bar within bar and a nuclear bar. And this nuclear bar arrives when you have this concentration of mass in the center. Here you see a diagram where there is the frequency, omega, versus the radius. Omega is only the rotation velocity over r. So each time you measure the rotation velocity in a galaxy, you can compute omega. And kappa is the epicyclic frequency. It's only some function of the second derivative of omega. So as soon as you measure the rotation curve, you can compute kappa and omega minus kappa over 2 and omega plus kappa over 2. All these frequencies are plotted there. And this omega minus kappa over 2, you can show that it is the processing rate of all these elliptical orbits that I've shown previously. So this is the processing rate. And of course, when all these processing rates are common, they, with self-gravity, are pushed to a density wave, which is a constant omega. So when you have a pattern speed omega p here, you can see that when it crosses the omega, you have a corrotation. And when it crosses these, you have inner limb blood resonance and outer limb blood resonances. And after a while, if these curves come up and up because of the mass concentration, you will decouple the secondary bar, which cannot grow at the same or rotate at the same pattern speed as the big one, and it will be a very fast nuclear bar, like in this simulation here by Friedli et al. The stars are in red here, primary bar, and the secondary bar, which is perpendicular, and you see the gas behavior in this big bar and the nuclear bar. So you need this secondary bar to prolong the action of the primary bar and to fuel the nucleus. So this is important. And then you can also compute the torques in this situation of bar and nuclear bar. And I just draw this a very simple schematic drawing just to give you intuitively the sense of the torques. In fact, when you have a bar parallel to the horizontal axis, for instance, you have the bar splits the space in 4 quadrants. And the forces here, if you have a spiral galaxy rotating in the sense, direct sense here, you have this trailing spiral outside of the bar. And of course here, the red parts of the quadrants here, you have a force that restored to the potential well, which is along the bar. So the tangential forces are like that. And the torque is due to these 2 tangential force that is positive. Of course, here they will be negative, but the gas is not concentrated here because the spiral structure is there due to the crowding of orbits. So of course, if you have a completely axisymmetric gas distribution, the torque will cancel out in one orbit, but here you can see that you have positive torque. So the gas from the bar to the outer parts will be driven out and will accumulate at the outer limb blood resonance, and you will have a ring at OLR. And if you prolong this spiral structure inside the bar here you have the dust lane, characteristic dust lane that you see along the bars generally. And you see now that the spiral structure, most of the gas is in the other quadrants, the blue quadrants here. And the torque is now negative. It has changed sign. So you will bring all the gas from corrotation to the ILR inside. And then it will stop there, waiting for a nuclear bar. So you see, you can have the sign of the torques, and you can have also quantify this this torque by measuring the forces and applying to the gas distribution. When you have a galaxy, how do you compute the force? In fact, you assume that inside the few kiloparsec of the galaxy, the dark matter is negligible, so the potential is due mainly to the stars. The gas is also a small fraction, so you can neglect the self-gravity of the gas. And then you take a galaxy which is almost face on, or 40 degrees, not more. And then you take a near-infrared image. Near-infrared image to have the old stars that make the most mass and have the potential. And then from the density, deep project to have it face on, you derive the density, and by the Poisson equation, you derive the potential and you derive the forces. So here you have this kind of a picture at the top right here. You have the bar in this direction, which splits the space in 4 quadrants, as I've already discussed. Here in red, you have the positive torques, in blue, the negative. And then you superpose the distribution of the gas. The contours here are the gas measured with the plateau de Buhr interferometer that is now called NOEMA because it has 12 antennae instead of 6. And then you see that most of the gas is in the blue quadrants, which is negative. And then when you average out at each radius, you have this curve. So this curve is plotted the angular momentum transfer relatively dl over L in one rotation. And you see that it goes to 30% maybe. So in one rotation, you can lose 30% angular momentum, and you can extrapolate that in 3 rotations, the gas will be driven inside, let's say 10 parsec of the resolution of the observations. So this was the computation that we did in a project that we called NUGA, Nuclei of Galaxies, with Santiago Garcia Borrello. We observed about 20 galaxies, and in only 1/3 of these galaxies, we discovered that the torques were negative, so driving the gas toward the center. This was at the scale of 10 parsec because of the resolution of the plateau de Beer. But still, it gives some information that most of the time, 2/3 of the time, there is positive torques, and gas is stored in the ILR. You see an example here of 6951, where there is inside the bar, there is a nuclear ring, and the ring is indeed devoid of gas, at least in CO. And we have to wait that, for instance, in the top right here, you see 3 snapshots of a simulation, large scale and a zoom at the small scale at the right, where you have first accumulation of the gas in the ring, and then progressively the nuclear bar is developing, and the ring is depleted of its gas towards the center because of the nuclear bar. So you are waiting that the gas is decoupled and comes to the center. So this was at least what we obtained with 100 parsec. And of course, we had not the resolution to look at what happens at 10 parsec scale, because here you see that there was still some dust here and maybe some CO in the center. But now we are going to have this information with ALMA. ALMA can have 10 times more resolution, especially in CO322 in band 7. So in a cycle 0, we have begun to observe this kind of barred galaxy. The first one was 1433, and we had cycle 0 resolution, not yet the maximum. And you see there is here a barred spiral, a very clear dust lanes, which are the spiral structure inside the bar. And you see with HST, which is also in blue here, the one ring, which is the ILR, the inner line branch resonance. So the gas is accumulating there. And what we saw with ALMA is the orange or red here that we superposed with HST there. But we saw this second ring. In fact, there is one ring here and the second ring. And the gas is not yet completely in the center. In the center, we also saw in the minor axis, we had evidence of a small outflow of molecular gas at 100 kilometers per second, which is very mild. And 7% of the mass was in this flow. So it was the smallest flow detected. But as for the feeding, it was not completely convincing that it was feeding, at least maybe in the past, but not now. Because here you have this decomposition of the face-on galaxy with a bar and the 4 quadrants, positive in red, negative. And you see that finally, when you compute the dl over L in one rotation, the center, of course, is perturbed by the outflow, but it's never negative. So we have a positive here, and positive means that the gas is driven outwards to pile up in this ring. The second ring, the first ring is there at the border of the field of view of ALMA here, which is 18 arcsecond with the CO322. And still, we have not really good evidence of the feeding at this scale. More the contrary, we have the accumulation of gas in the second ILR. Well, the second galaxy we observed with ALMA was 1566, and this one was really more convincing. We had a Seyfert one here. You see a barred galaxy at large scale. What we're observing is this square, which is exactly where the ILR ring is. Here's 4 minutes. We have a field of view of 18 arcsecond. So the ILR ring is at the border. We are missing some sensitivity for the ring. But inside, we see a very surprising thing that the velocity field is rather regular, except some streaming motions due to the nuclear spiral. But there is a nuclear spiral very clearly. And what was surprising is that it is trailing. You see here the trailing arms. The omega is in this direction, and here is the same direction as the outside arms, is trailing arms. And why are we were surprised? It's because if I come back to the elliptical orbits of the stars, here is the stars orbits, stellar orbits in the rotating frame of the bar. The bar is parallel to the horizontal axis again. And here you have parallel to the bar inside co-rotation. At co-rotation, there is no term. And outside, it's perpendicular to the OLR. And what we're expecting inside the ILR, but you see here in the top right that omega minus kappa over 2 is the precessing rate. So when the gas loses its energy by collision, it comes here and it's precessing more and more rapidly, going to small radius, until the ILR at the peak here. And afterwards, it's precessing less and less rapidly. So here it's taking some advance, and here is trailing again. So we were expecting, if there is no black hole, there is no the peak, Kepler peak in the center, that you have a leading arm inside the ILR. So we were expecting that. And in fact, we see the reverse. We see a trailing nuclear spiral. And this is what is expected when there is a black hole. And the omega minus kappa over 2 is climbing again because of the Kepler potential, which is in 1 over r, and every frequency is coming up again to infinity. So this means that the gas we observe here is under the influence of the black hole, and most of the gas is here, and it is trailing again. And if it is trailing, we expect that the torque is negative. So it's really fueling, the gas is fueling the black hole. And we can confirm that by computing the torque. As I've shown here, the bar is there. There is the positive torque in red and the negative quadrant in blue. And you see that this nuclear spiral in the face-on view is exactly in the blue zone. So the torque is negative, and when you average in radius, you see this negative torque here. So indeed, we have confirmed a very neat feeding of the black hole, and you see it's a very strong amplitude. It's 40% of the angular momentum is lost in one rotation. So indeed, we see the evidence of feeding. And it's not on the only galaxy where you saw that. We saw that in NGC 613, 1808. 1808 is an example here. You see a 50 parsec scale. At this scale, we see this nuclear spiral. It's still the CO322. We see also in the dense gas tracer, here is HCN 423 that we observed simultaneously in band 7, HCN 423 velocities. You begin to see that the velocity field is distorted. It's not the same position angle, and I will come back to that because a reorientation of the molecular torus. The beam here is 4 parsec, it's 0.08 arcsecond. And you need this beam of 0.08 or even less if you want to see this nuclear spiral structure. You see, Salak et al. Have looked with ALMA in 1808, and they have not seen that. They have seen the ring at the ILR, but inside they had not been able to see a nuclear spiral. They saw the velocity field, and they saw also an outflow at large scale, because in this galaxy there is a dust lane perpendicular to the disk, and it's known to be a galactic wind galaxy. We also saw this nuclear spiral in 613. You see here at the ILR, the ring at ILR, and Miyamoto et al. With low resolution see also that with ALMA, but in the center they had not enough resolution to see that, the small nuclear spiral. Here, when you make a zoom, here you see that the scale is 10 arcsecond with the ring and the velocity in the ring. And here we make a zoom by a factor 10. It's only 1 arcsecond there. So the contours are the CO322. You see the nuclear ring here in contours. And inside the ring, you see here the continuum, which is synchrotron, which is the AGN. And we'll also see at the same scale the HCO plus that we have at the same time. And the HCO plus is exactly this scale inside the nuclear ring. And inside the nuclear ring, you see the velocity, which is a red and blue part is almost north-south, while at large scale, it was almost east-west. So you see there is a different position angle and certainly different orientation of what we call the molecular torus. Molecular torus is inside the nuclear spiral. It's very small, it's 10 parsec scale, and it is a different orientation. I will come back to that also. So when you compute the torques here again in this nuclear spiral, it is negative. It's the same case as before in 1566. And you see that in this region, nuclear spiral, you are really feeding the nucleus. That's this time you are losing all your momentum in one rotation. So it's very efficient. And it lasts about 10 million years. So this was for the feeding. Now we understand better how the feeding is done by the gravity torques of the nuclear bars and nuclear spirals. And now about the feedback. In the same galaxy NGC 613, we saw also an outflow. And here you see the PV diagram at the top right. You see the velocity and the major axis, and you see how steep is it in the center. Not this clump, which is the H13 CN, so you forget about that. But this one is a very steep gradient, and the normal gradient is there. So you see that. And here you see that indeed this direction here is also the flow that we see, the blue wing and the red wing of the CO gas is in the same direction as the radio jet that you see with the VLA. The black contours here are the VLA jet. And when you make a zoom, you see that the blue and red outflow of the gas is indeed in the direction of the radio jet. So, and the outflow velocity is 300 kilometers per second. It's a little larger than the previous one. And we have the m dot at the m of radiative, 15 thermas per year. So it's a rather common phenomenon to see the outflow. And in low luminosity AGN, we see that for the AGN jet. In 1808, we have not seen at small scale any outflow. You see here, there is no outflow in the major axis and minor axis PV diagram. Although people have seen an outflow farther away, larger scale, and we think that this outflow is due to starburst. If it was due to the AGN also, it would have been seen at 10 parsec scale, but we see that only at 100 parsec scale. And we have enough scale resolution now to distinguish the starburst and the AGN influence. Here we see also the diagnostic of lines, HCN over CS and over HCO plus. It's well known that the HCN is enhanced in the XDR region where we have X-rays. And you see in the red, the AGN close, molecular gas close to the AGN, which is large in HCN. And when you are at the farther distance, you are in the blue zone, which is dominated by starburst. So you need really the high resolution to distinguish this region. So I have already mentioned that you have two ways to have this feedback. You have what we call the quasar mode. When you have a very high luminosity AGN, quasars are at high redshift. When the luminosity is close to Eddington, then you have radiation pressure that can push a wind of gas, and you can have this kind of feedback mode. But for low luminosity AGN, which is less than 10 to minus 2 Eddington luminosity, and it is very frequent for nearby Seyfert because quasars are rare. And then in this case, you have the radio mode, which is, we think that it is the radio jets that drag all the molecular gas when it is not perpendicular to the disk of molecular gas, and it is frequently like that. Well, the only case of nearby Seyfert where you see both, you can see wind and radio jet, is NGC 1068 because it is a case of relatively strong AGN. high luminosity. And we see an outflow here. You recognize the spiral structure, which is almost face-on. You have this ring, which is at ILR, the first inner Lyman resonance. And then the AGN is not at the center. It is at this point here. There's an offset, it's like a M=1 perturbation. And also the jet is not perpendicular to the disk, but is perpendicular, is dragging some gas in the plane. Here you have a view, a schematic view of Hadron galaxy, where you have the ring here. The AGN is not at the center, and the molecular outflow is dragged by, because the jet is in the plane of the galaxy. Not completely, but at an angle. In fact, it's known that the NGC 1068, the CFR2, and you need a dusty torus or molecular ring to obscure it, and it is almost adjoint. So it's not the same orientation as the main galaxy, which is almost face on. But the jet is in this direction here, and it is pushing the molecular outflow that we see. And here you see that the ring is here, and the AGN and the molecular torus is there. We have been able to do the CO625 in this galaxy, so high resolution. In the CO625 at high frequency, you see the dust continuum. And the dust continuum in the millimeter is a contours here. It's orientation perpendicular to the disk, molecular torus, which means that it is in the polar direction. It's like what we see in the mid-infrared. It is in the polar direction and not in the dusty torus, in fact. CO625 needs more density, so you have a small torus. You see better in CO221 at high resolution here, that indeed you have this direction of molecular torus, which is perpendicular to the jet and to the polar direction. The torus is about 3 to 5 parsec. It depends, of course, on the CO line that you observe. And if you compare to this beautiful picture by Sphere, which is a near-infrared, and it's beautiful because it's the polarization map, and the difference between the polarization and the axisymmetric and centrosymmetric thing. So you better see the perturbation here. And you see that indeed you have a polar dust here, hollow cone, in fact, like the model I've shown in the first slide. And you have this perpendicular disk. And when you compare with the CO contours, you see that exactly the same kind of molecular torus that we see here. And indeed, the current density of the molecules is enough to have a quantum thick disk here. And it is not the dusty torus that obscure the CFR1 to become a CFR2, but it is molecular torus. And it is a general picture, one you see in the near-infrared, 1068. In green, you see the direction of the polar axis. And in red, you see the mid-infrared, the dust in mid-infrared. And you see that indeed the dust in the polar direction and not in the dusty torus that were expected for several years, in fact. So in 149 AGN survey, there was 21 showing this polar dust characteristic of wind, in fact, wind and outflow. Now I was mentioning the radio mode for our low luminosity AGN, and there is one which is very spectacular, is the one in NGC 1377 that we were observing with Susanna Alto as a PI here. And we did several resolution maps. In fact, we need to have several steps in the scales to better understand this outflow, this molecular jet, in fact. So the galaxy is almost east-west, and what you see in color is the wings of the CO line. So blue is the blue shifted line, red is the red shifted line, and in gray you have the more systemic velocity gas. You have the impression that there is a cone also, there must be a wind maybe. And this jet is very, very collimated. You see in the dispersion, the jet here, the CO dispersion. And what is surprising also, it's blue and red, but then it becomes red and blue. So it changed sign. And this is certainly because the jet is almost in the plane of the sky. So it is just sufficient that it is precessing by 10 degrees to be either precessing from you or coming towards you. And certainly from here to here, it has been precessing. And you see this kind of precession. When we went to higher resolution, you see how well collimated it is. And it is really a surprise because the jet is not seen. There is no radio jet. In fact, when you look at the VLE map of this galaxy, you see only a core. And the core is very weak. There is no jet. And we call it the most radio weak galaxy. Why? Because there is a relation, very well good correlation between the infrared and the radio flux in galaxies due to the star formation. And this is one of the very good correlation. So we could expect much more radio emission in this galaxy from its infrared flux. And we see much lower radio emission and still only a core and no radio jet. So this is very surprising. So maybe the radio jet has disappeared. It was relativistic and has gone away in 10 million years. And now we have only the dragged the molecular jet that is much slower and still there. We don't know, but of course, it must be a transient thing. And in the jet, there is 10 to 7 solar mass of gas. In the cone, there is 10 times more. And this size is about 100 parsec or so. So it's not a very large jet, but just to understand the principle, the mechanism doing this jet is quite complex. And we think that it is, you need a radio jet first because it is the plasma that can be trapped by the magnetic field that is rotating fastly, and then we can trap and confine the plasma in this cone, very collimated things, while the molecular gas could not. So we think that we need this radio jet. And for the precession, we think that it's like the example of the microquasar SS433, sorry. And this was seen more easily because the scales are much shorter for microquasars. And you have seen this precessing by 10 degrees. So we make this kind of model for 1377. And this is observation, this is model, and it fits rather well. We don't know exactly the angle, but the velocity of the outflow is between 250 and 600 kilometers per second. It must be launched at 10 parsec also. So this galaxy was an example where there was first the wind, like a cone, not collimated at all, and the jet. So we could have the jet and the cone at the same time, the wind and the two modes of feedback. Now I want to go to the molecular theory that is one of the new results that we have seen with a high resolution with this ALMA data. I've just recalled what I've shown you about 613 and about this nuclear spiral and the molecular torus. So we call molecular torus this small scale disk, which seems decoupled, in fact, from the rest because of the orientation. I just mentioned the velocity position angle here, which is completely different from that. So there is some decoupling, and it helps us to define a molecular torus. There is also the same kind of thing in many galaxies, like 1326. You see, this is a barred galaxy. There is a nuclear ring inside at the ILR. We see it in the colors. And in HST, it's a nuclear ring which is forming a lot of stars, a lot of gas. And when we look at with ALMA, this ring is this big one, which is at the border of the field of view. And inside, we see this molecular torus, which in maybe it's something more edge-on than the rest, so different orientation. We see that also in NGC 1365, the well-known beautiful spiral with dust lanes. Here you see the dust lane with ALMA. And inside this ring here, inside at the point here, you have this, which seems more face-on than this, and which at least is a hole in the center. It's really molecular torus this time. And it's the same kind of scale, decoupled from the rest. And we can, for the 8 galaxies that we have observed with such a resolution, we can derive that there is a torus for 7 out of 8 of them. Radius typically 10 or 20 parsec. mass of gas is 10 to the 7 or so, and mainly the inclination of the torus on the plane of the sky is different or random with respect to the inclination of the galaxy. Now, to which mechanism you can attribute this misalignment? In fact, there are many mechanisms possible. In the literature, when you look at the theory of the interpretation, there are many mechanisms. I just cite some, at least at small scale, when you have radiation pressure acting on the accretion disk, you can have this warping instability. Here you have in the center, imagine that you have a radiation pressure impacting already warped disk. And of course, this disk, if it is optically thick, will re-radiate in a direction which is not radial. So there will be a torque, and this torque will maintain this warp, and that will be a warping instability. This was simulated by Melanie Begelman, in the center. This is a well-known mechanism. There is also magnetic instability, and there is also this well-known Bardeen-Peterson effect that has been recently resimulated here. This is due to the spin of the black hole, which is not oriented at the same direction as the accreting gas around. It can be there not only on the accretion disk, but until 10 to the 4 Schwarzschild radius, that is about 1 parsec or so. And what happens is that you have a relativistic effect, like the lens stirring effect, that rotates the frame, and that is the black hole drags the matter around it and force it to rotate at the same angle. So it tried to make a torque on the gas to reorient and to be aligned to the black hole spin. And here is some simulation by Neil et al. With different angles, 30, 45, and so on. And of course, it depends on the viscosity of the gas. If the gas is viscous enough, it can be only bent and gradually warp. If it is not, then the disk can break, and can break in several subrings. And like recently, the sketch of Pounds et al., for instance. And if you have several rings, it's even much more efficient to fuel the AGN, because these rings will precess differentially, and they will collide, and they will cancel out their angular momentum that is not aligned. And then you will have a large efficiency to fuel the AGN. So this is quite interesting to have this mechanism very close to the black hole. That's what we see also in warp maser disk when you are at a small scale. It is seen in a 4258, which is one of the prototype. You see the maser disk here. You see it also in 1068. This is a very well-known Gallimore et al. Picture, where you see the points where it's redshifted and blue shifted, but it is warped. And Martin had done this simulation for 4258. For 1068, it was also simulated by Caproni. And the advantage of making this simulation is that you can quantify at the time scale to realign the gas to the black hole spin. And this takes about 10,000 years. So at least it's very short, as soon as you are at below 1 parsec, and it will realign. Of course, in this realignment, you will have an exchange of angular momentum between black hole and the disk, and the black hole also will be reoriented by this. But it is quite interesting to see that we expect a lot of misalignment at small scale, in fact. There is also an advantage to have this high resolution, because we have shown that this gas is under the influence of the black hole. So we could hope to measure the mass of the black hole more precisely than with the M sigma relation, for instance. And this is an example of NGC 1672, where indeed inside the ring you have this nuclear disk, which looks edge-on, and you have the HST image. It's the galaxy is more face-on, but you see that the molecular torus is edge-on, and you have a large velocity gradient. When you make the position velocity diagram, you have this scale here, gradient of almost 400 kilometers per second in 20 parsec or so. It's very high, velocity gradient. If we model the rest of the galaxy with the near-infrared image, you expect only this kind of gradient here. So you need to add the black hole to take into account for this observation here. Here you have this Keplerian peak here, joining back to the bulge and the rest. So you see that we are able to derive how much mass, and here it was 5×10⁷ solar mass that you have to put in the black hole to represent the observations. And of course, not only on one dimension, you can do in 2 dimensions. Here I show the modelization that we have done for these 8 galaxies. You see that with the bulge in red, what you are expecting for the velocity of the disk in blue, the bulge in red is 2040 parsec. And you see that we are really dominated by the black hole because the rotation curve is the black one. The bulge is dominating, but the disk is completely negligible at this scale. So when you make the model at 3, this model was only axisymmetric. There was no bar, no perturbation. That's why the velocity has not this S typical of a bar, a nuclear bar. But at least we can reproduce the right velocity gradient and the moment 1, B, and sigma. The sigma is not quite because there is more gas in the center with the model, and we have to change a little bit the model. The same kind of modelization for 1365. So velocity field for this molecular torus and in the model and the observation. So at least with the cube of data, it is more easy to represent the mass of the black hole. We can compare with what have done the team of the Wisdom project. They have done this kind of measurement of mass of black hole, but with more massive galaxies. With more massive black hole, now it's 10⁸. So these galaxies were early types, and of course they need not as much resolution because of the mass, higher masses. And you see that in the PV diagram, without black hole and with black hole, they can indeed represent better with a black hole with this kind of PV diagram here. Sometimes there is a hole which is not welcome, but sometimes the gas goes to the center. And with all these galaxies, you can make a summary of this M sigma relation that here are the early types massive galaxy in blue. And here are our 6 galaxies that we have been able to do this when there was enough gas in the center. And the molecular torus was almost adjoint. And of course, there is more scatter in the small mass than in the high mass. We don't know yet if the scatter is due to the difficulty to observe it because, of course, smaller mass of the black hole are more difficult, or is it intrinsic scatter? If we have more of these direct measurements of mass of black holes, we will be able to see, to say if it is intrinsic or not. Now I want to finish to explain why we have to expect that there is a non-alignment. It is expected because we have observed that in several times. At least there is a very good example of 4258, this one where the maser of H2O was seen. This is a special galaxy where the jet is inside the plane of the galaxy. You have in red the H alpha image, so normal spiral arms, and in blue is the anormal spiral arms. In fact, it is a jet, and the X-ray gas also has the same kind of morphology. And why? Because the jet is in the plane of the galaxy and it is deflected by the molecular clouds of the galaxy. So it's good evidence that the jet, which is perpendicular to the accretion disk, is not at the same orientation as the main disk. So there is a decouple of the molecular torus, certainly at the center. The Milky Way, of course, an example, we see the Milky Way drawn. And when you look at the center, we see in orange this HCN circumnuclear ring, which look more face-on than drawn, and also this mini spiral, which is in green here, which looks also more face-on, at least 40 degrees, and not 90 degrees. So there are many examples like that. And also, an example which can give an explanation is that also we can have accretion at any angle. In fact, there is the 10 parsec scale. You can have a molecular cloud arriving at any angular momentum. And we see that in NGC 1068. This is a work by Imaneshi et al., a recent work with ALMA also. And I've shown already this ring at the ILR, which is rotating. The west is red and the blue is east. And when you look inside at this around the AGN, which is not at the center here, you look at the scale 5 parsec instead of 140. And this is a reverse. In west, you have the blue, and in east, you have the red. So you have a counter-rotating gas in the center, while in the maser disk, even smaller, 1.4 parsec this time, you have the red, you recover the red of the ILR, red and blue. So inside you have a kinetically decoupled completely here, and you recover the orientation here. So it can be explained only in a recent accretion of gas, which was at different angular momentum. And this, you see that very well in the HCN image, which was done with ALMA with 0.02 arcsecond resolution. You see that the counter-rotating disk is the outside of this molecular torus. Inside is normal. Here you see the blue and the red, and inside the red and the blue. So in the same molecular torus, you can have these two counter-rotating. That's why in 1068, it has always been very difficult to find in the rotation of the molecular disk, because when you had not enough resolution, you smooth out this to almost zero velocity. You had the impression that it doesn't rotate, and it rotates, but in two different sense. Here you have the expected thing, blue and red, and you see how it is counter-rotating at some point. And of course, when you look at the accretion, again, it was prograde rotating in the maser disk. You can also see that in simulation. Here you have a simulation of the Milky Way that we done with Renaud and Salem et al. And in the center, you have a bar. Gas is driven inwards. When it was strong enough, it makes a starburst here. And of course, a fountain effect. You have gas going up of the plane and then come back after the fountain effect. And after coming back, it comes with a polar ring. You see a disk which was very stable, and it was perpendicular in the face-on direction. In edge-on direction, you see the polar ring relay. It's like that. And of course, if it was not polar completely, it would have reorient, warped, and come to the equatorial disk. And when it is polar, it is relatively stable, and you can explain this kind of inclination by orientation. So in summary, I can say that with ALMA, we have been able to discover the fueling mechanism, which was a nuclear spiral, which was a trailing spiral and fueling directly the AGN nucleus. We have seen also in some cases molecular outflows, certainly due to AGN, at least in 613, and in 1068 we have both the wind and radio jet. And also we have discovered molecular tori in 7 out of 8 galaxies. And the main feature is that the molecular torus is always decoupled, not the same inclination, not the same PA. And with the small scales, you have evidence that there has been accretion with a different angular momentum, and or there have some warping instability due to radiation-driven things or the Barton-Peterson effect. So thank you very much, and I'm waiting for your question.
Thank you very much, Francoise. That was superb and amazing, the amount of physics that you crammed in that talk and your observations. So let's open the floor to questions. Please raise your hand. Sturl.
Yeah, so I had a question about the torque maps in the first half of the class. Can you describe a little bit what the sensitivity to the uncertainties in those are? I assume you take infrared light, assume a constant universal mass to light ratio. You have some assumption about no bulge and a vertical scale height, no warp, so you can deproject things. You neglect the gas and dark matter. So what do you think are the uncertainties?
Well, the uncertainty in the bulge, when there is a bulge, we subtract it before deprojecting to face on. Because the bulge, we assume that it is more spherical or spheroidal. So we subtract and we put back, but we deproject only the disk. But of course, it's an uncertainty because we don't know the flattening of the bulge. So I agree that there is a, but the galaxies that we are doing that have a small bulge in general. So we think that's not a big effect. But I agree that in the center, well, what we do is 1 or 2 kiloparsec. So it's not, in general, in galaxy, you can have M overall varying, but over 10 or 20 kiloparsec. If you're just inside 1 or 2, we keep M overall constant, and we calibrate in having the right rotation curve. So you can calibrate the M overall. In general, in the infrared is smaller than 1. But we think that when we normalize then to the rotation of the angular momentum L, because we calibrate the exchange of angular momentum in relative quantities, dl over L. So if we are wrong by the rotation curve, it's divided, if you know what I mean. So we the quantity that we derive is how much in one rotation we change in relative angular momentum, is not depending much on the rotation curve that we assume. Imagine that we are wrong by factor 2 in rotation curve, then it will cancel out in the dl over L. We hope. But I agree with you. There is some uncertainty there because there is nuclear bars, not axisymmetric, and we don't know exactly the rotation curve, the true rotation curve. We have the rotation, but we have not the circular velocity. Well, that's the best what we can do. Of course, we assume the near-infrared image, in general, the NICMOS HST, which are the old stars, and we neglect the dark matter. But inside 1 or 2 kiloparsec, I think we are dominated by baryons.
Okay, we have a question from Catherine.
I just had a quick clarifying question. When you said that when you compared to observations of the Milky Way, which feature in the inner Milky Way was similar to the molecular torus in other galaxies?
Well, in fact, what I was comparing is for the inclination. There was a nuclear, I've not seen the molecular torus in the Milky Way. I see the circumnuclear disk, which was the orange feature in AGN, but it was a hole in the center in the molecule, at least in AGN. So I don't see the molecular torus there.
And but if there was one, it would be within that.
Yes.
Okay. And so what size scale would that be for the Milky Way?
10 parsec, I would say.
Thank you.
Okay. More questions. I was going to ask, to what extent does the phenomenology, particularly for the Seyferts, can that be extrapolated to more energetic, like quasars?
Yes, for quasars, well, if you're thinking of feeding or feedback, for feedback, the quasar will be the winds more than the radio jets.
Yes.
That what we have seen is collimated molecular outflow, and there would be more wind, which is not collimated. But for the feeding, it's possible. The quasars are in general in spiral galaxies, and there could be bars and well, at least for high Z quasar, because the quasar now are more due to interacting galaxies. So you can, but interacting galaxy can also trigger a bar formation. We see frequently in interacting galaxy, a bar is forming because of the tidal torque, which trigger the bar. So at least at the end, a bar should be there, a bar or nuclear bar, because if it is axisymmetric, you have nothing to transfer angular momentum.
And the duty cycle is determined, you think, by the dynamical timescale for these.
And for the strength of the bar, of course, because if it is a weak bar, it will take much more time because it's almost axisymmetric, and asymptotically, if it's axisymmetric, you have no torque at all. So the gas will maintain its circular rotation. So it's still a strong function of the strength of the bar. If the nuclear bar is strong, you can have one rotation and everything is one rotation at 1 parsec scale. If it is a weak bar, you have to wait 3 or 10 rotations before having your gas in.
Okay. We have a question from Anila.
I think we have. Okay, there I am. Yeah, I actually, this is more of a comment, so I wanted to leave it till the end. I really enjoyed your talk very much, Francoise, and I found the observations and the interpretation really very inspiring. I was really interested in how this had come about and the observations you put together. But I also wanted to comment that you must have the same sensation that I do with the results that are coming from ALMA, in the sense that I did my thesis observations on the aerospace telescope, and I didn't know anyone. I know very few people who made very
interesting.
So I was reminded when Chris said that you used the aerospace telescope that the results from ALMA are so unimaginable compared with the way we began, that it's wonderful to actually be seeing the fruition of a field in this way at a time when when one is still able to do research into it.
Yes, I agree. It's fantastic, really fantastic. When we see these images, we are stunned. Yes, what a progress in all these years.
Unbelievable, unbelievable.
Fantastic.
All right. Well, that. Do we have any other questions? That might be a good place to make a transition. So if there are no more questions, we will. The faculty should stay on for the